Hey everybody. So I'm going to do a little video here to give us some help on a problem someone asked about. So I'll start by explaining the problem, and then I'm not going to solve it totally, but I'll get us a good portion of the way there towards solving it, let's say. So here's the situation. We've got a little pool here, and I'm imagining there's a dog tied up. Right, so this little red dot I'm putting in is going to be the point of contact. It's a leash that's tied to the pool, and the leash is such that if the dog runs straight around the side of the pool, right, it can get exactly to the opposite side, and that's exactly how much leash there is. Okay, and the question is, how much running area does this dog have, right? So this green line is supposed to be showing us if we were to run around with the rope at full extension, how much space would this dog have, or how much space would that shape in circle? It's not a circle. Anyways, encapsulate. Anyways, I think we got the idea. So a few things I want to do. First of all, I'm going to skip a couple easier parts of the problem. So one thing we should notice is when we're over here on this right half of the circle, right? This over here is just a circle. Oh, sorry, I want to put in one other thing. We're just going to call the radius of this pool R. Okay. This half of the circle here, this is a circle with radius equal to the leash, right? Whatever the leash is, just traced out this half of the circle, right? That's, I think, apparent from this problem. And so we can find the leash length easy enough. The leash length, of course, is just half of the circumference of this circle. So a circumference is 2 pi times the radius. So in this case, it's pi times big R. So the radius of this large green circle, or half green circle, is this whole thing is the radius of that. So you can figure out the area of that pretty straightforward. We already know how to find the area of half of a circle. So I'm not going to worry about that part of the problem. What we have to notice is that when we get to this side, to the left half of this green shape, it becomes more complicated, right? So I've drawn in here, for instance, as the dog kind of pulls itself as far as it can around, it's blocked by the pool. So it loses some leash length to the pool, and then it pulls out as far as it can. And so it's hard to kind of understand how that shape's going to be. That's what we're going to concentrate on. And I'm only going to look at the top half, right? For symmetry reasons, I know I can just double, right? My goal is to find this area. If I find the top area, I can find the bottom area just by doubling it. Okay, so that's our job. I do also want to I want to kind of take a moment to prove a couple of facts that we're going to need later in this problem before we dig into it. So let's leave the setup of this problem for a moment, and I want to prove a couple of quick facts. First of all, I want to prove that if I have a circle and the tangent line to a circle, the top half of the circle, that the radius to the point where the tangent line touches the circle is perpendicular. Okay, this is pretty easy to prove. The equation of the top half of this circle is going to be y equals 1 minus x squared. The square root of that, or let's actually write it as 1 minus x squared to the 1/2 power. Okay, so first of all, let's say that this point right here, let's just give it coordinates x, y. Well, first of all, what's the slope of the radius, the line that's drawn from the origin to that point? So I'll just call it the radial line. Well, it's the change in y, and we're connecting it to the origin with coordinate 0, 0. So this is going to be y minus 0 over x minus 0, right? So it's just the ratio of the xy coordinates. That's the slope of the radial line. Let's look at the slope of the derivative at this point. Well, y prime is going to be 1/2, 1 minus x squared to the negative 1/2 using the power rule, and then the chain rule gives us a negative 2x. Y prime, if we simplify and write this as a fraction, the 2's will cancel. I'm going to get negative x over 1 minus x squared to the 1/2. But 1 minus x squared to the 1/2 is just y. So y prime is equal to, oops, let's write down here. Y prime is equal to negative x over y. Okay. So this is the slope of the tangent line at any point along here. And what we notice is it is the inverse, opposite reciprocal to the slope of the radial line, right? Y over x becomes x over y, and we add a negative. And there's a geometric fact, and this one I'm not going to prove. I hope this is somewhere lodged in your memory, that the slopes of lines perpendicular to each other have exactly this relationship. If line 1 is perpendicular to line 2, then the relationship between the slopes is that, which is exactly what we have here. So I'm going to assume that fact from way back when, and that's why we know the radius. One way we can know that the radial line is going to be perpendicular to the tangent line. So we're going to use that fact a little bit later. Another fact I want to use is the relationship between angles and arc lengths of circles. So really, this is just going to come straight from the definition of a radian. If I have an angle, theta, and I want to know its radian measure, if I put that angle at the center of a circle, so that this part of the angle is at the center, and that circle has radius r, and then when you put the angle at the center, notice it won't matter where I put it, it's going to trace out some length of the circle, right? There's this arc length here, okay? Let's give that a name. Let's call that L. Well, theta is defined to be the ratio of the arc length to the radius, right? As the arc length gets larger, you can imagine if I'm opening this angle, the angle's getting bigger. Or you can imagine an arc length of 0 when this angle is snapped shut. We get an angle of 0, right? Should also tell you what 1 radian is. 1 radian is the angle so that the arc length is equal to the radius here, okay? Well, this gives us a nice formula. If we're measuring things in radians, the arc length is just equal to the radius times the angle measure, okay? So that's another little fact I'm going to use a little later in this problem. So I just wanted to establish those two things. Arc length is equal to the radius times the angle measure in radians. And so the phrasing is something like the arc length subtended by the angle. I think that's the word that means this picture. Is equal to the radius times the angle in radians. And then that a tangent line to a circle is perpendicular to the radial line to the point on the circle where it touches, where the tangent line intersects. Okay, so we're going to put those in our back pockets for now and go back to this problem. So let's jump over to another little animation I have to help us understand this picture once again. So remember what I said. In this picture, I am ignoring what's happening on the right half of the circle. I'm going to concentrate on this, on the shape defined over here, right? I'm right now only worrying about finding this area, okay? All right, because this half is a semicircle. The bottom half is the same. So that's what we boiled the problem down to. So with that in mind, let's switch gears for a moment. Here we are with that same picture, but what I have going on here, so here's the red dot is going to represent, right now it looks like it represents where, and it does represent where the leash touches the pool. Now imagine this dog trying to run, right, towards, let's say, towards the left in a horizontal way. Well, what's going to happen is, as it moves left, part of the leash is going to start bending around this circle. And so what we'll get, right, so now that red dot is representing the last place that the leash touches the pool as the dog runs as hard as it can to the left, right? The dog's getting pulled and pulled and pulled. And now the dog's going to continue trying to run down, and it just keeps getting pulled closer and closer, right? More and more of the leash is now wrapping around the circle until we get to the very end, and the entire leash is now wrapped around the circle, and halfway around the circle, right? And so this little blue dot here is, if I go to 0, it disappears because the slope becomes 1 over or something over 0. And so it can't draw that line for me, so I'm stopping near 0, but you get the idea. That blue dot represents the dog's path when it's as far out as it can go. Okay? So let's name a couple of things. Remember, what I'm really trying to do right now is find parametric equations that can describe the path this blue dot takes. Right? So I've already done it. That's how I'm programming this, but let's pretend I haven't and just use this as a little learning tool. Let's name a couple of things. I'm going to I'll use the notation I've used to program it. It didn't let me use theta. So I'm going to call the angle in here. So let's call A equals the angle at the origin. And we're using our standard operating procedure, right? So A is this angle right here, measured from the horizontal axis to this blue line as it moves around, okay? So just to point out, A is going to go between 0 and pi, right? By the time it gets to the other side, that's an angle of pi, okay? I'm gonna erase this because we're gonna move the animation sometimes. So that's measured at the origin. There's another angle. So sorry, I'm gonna keep this idea for now. My first job, remember what I said, I'm gonna try to come up with a way to describe this point, the blue dot, but I'm gonna start by describing the red dot, okay? Remember the radius of our pool is R. I've had to decide on a value for R, so I used R equals 1, but just think of that as our units have become the length of this radius. So I want to describe this point here in terms of the angle A and R, right? R is a constant, and then A is going to be the parameter in our equation. Well, we have a very simple way to describe circles with parametric equations. The equations are always going to be R cosine the angle, so I've called my angle A, and R sine A. Okay. This is going to be the location, the last point of contact with pool by the leash. Okay, so again, imagine the dog kind of pulling out as far as it can. The leash wraps around, and this is the last place it touches it. That's what A represents. Okay, so what I want to do now, if I think about these separately, this point is represented by a horizontal distance and a vertical distance. If I can then figure out a way to write down the horizontal distance, the blue line is from the red, sorry, the blue point is from the red point, that combination will tell me the distance, that horizontal distance, that blue point is from the origin. So for instance, if I knew the red line was 5 units to the right, the red point was 5 units to the right of the origin, and the blue point was 2 units to the left of the red point, I'm going 5 units to the right, 2 units to the left. I must be 3 total units to the right from the origin for that blue point. So I want to now try to describe the location of the blue point, right, which is really our dog, relative to the red point. Okay. Right? So again, if I say the blue point is located negative 2 units horizontally and 5 units vertically, it doesn't mean the point negative 2, 5. It means 2 units to the left of the red one and 5 units up. And that's fine, because I know where the red point is, so I can just add those numbers to this. Okay? So let's look at that red point for a second. And I'm going to add something to my picture here. And just put in a horizontal line. Okay, right? So that line is going to stay horizontal the whole time we're doing this. And what I want to do is name this angle here. Call this B. Okay, let me clean up a little bit. I'm going to keep the radius label out of this for now. Oops, I need a pen. Okay, so the angle B is the angle from this horizontal line to the trajectory of the leash. Okay, so here's where I'm going to use that fact about perpendicular lines. If you notice this radial line, the trajectory of the leash lies along the tangent line, right? If instead of curving around it continued, it would only touch the circle at this one point. This is our tangent line right there. And so what I know is that it is perpendicular to this radial line. Okay. Well, what does that mean? That means, so we're gonna do a few things here. Sorry, I'm going to erase B again because it's going to get in the way from what I'm about to do next. So let's continue the radial line. Right? If this is the angle A here, this must be the angle A here. Right? I've just got this horizontal line is parallel to the x-axis. So the angle, right, these two angles are going to be the same, A and A. Well, what does that mean? This is a right angle here, so this is also a right angle on this side, which means this whole angle, which was B, is A plus pi over 2. Okay? And that relationship holds as we move around. It's like this angle is always, the purple line is always pi over 2 ahead of angle A relative to a horizontal line, okay? This is going to be a very nice piece of information for us, okay? So again, here's angle A. By the fact that we have parallel lines here, and we've got a line going through both of them, these are going to be the same angle. Then I'm just noting that I have a right angle here, so this total angle, which we call the B, is this little angle here plus the right angle here, which is a measure of pi over 2. Okay, so now I've got the angle right here, okay? So let's move over to the side here and do a little bit of work. This is my point, this is my red point, okay? Now, pretend I live on that red point. So as it moves around the circle, it's like us moving around the sun. We don't think about ourselves as moving around the sun. We're just referencing ourselves from the point that we're on. We're on that red point. From that red point, this purple line, right, is, right, which represents the location of our dog. Has an angle from the horizontal B, right? If I want to know the location of a point, all I need to know, let's give a name to this length right here. I'm going to call this length, I'll call it OH, it doesn't really matter, okay? So this length H, if I want to know the location of this point here, it's going to be H cosine beta, H sine, sorry, not beta, just B. H cosine beta, H sine beta, right? Just like we used the parameterization of the circle to tell us where this first point was living, relative to that point, this blue point, the one, well, let's use a blue on it. This blue point here, right, representing this blue point here, is out some radius at this angle. That's how you locate it. However, there's a big difference. H is changing. As we move around, H is changing. So we want to rewrite H so that it changes, right? And I want to understand how H changes relative to A, because A is my parameter. So I want to know, given an angle A, can I describe how long H is? And we can definitely do that. So here's how we can do that. So first of all, here's my parameterization of the blue point relative to the red point. It's in terms of angle B, but we already know how to connect B to angle A. We get A over pi plus 2, right? So here's the big idea. This length H is equal to the leash length, minus how much is wrapped around pool, okay? The leash length, remember, we realized was half the circumference of our pool, which is pi times, what did I call that radius? Just r? Okay, pi times r. The wrapped length, here's where I'm going to use that arc length formula I went over in the beginning. Remember, the arc length is just equal to the angle times the radius. So this is going to be A times r. In other words, H is equal to r pi minus A, or however you want to write it. Any of these are fine. Okay. So let's put this all together. That means the blue point relative to the red, meaning treating the red point as the origin in this, in how I'm going to describe the location, is located at, so I'm just copying H cosine beta, except instead of H, I get R pi minus A cosine of B, but remember B was A plus pi over 2. And then H sine B is R times pi minus A sine of A plus pi over 2. All right, we're not quite done yet. Because we don't want a parameterization of this blue point relative to the red point. We want it relative to the origin. And so now here's where we come back and use the original parameterization of the red point. This, so let's just think about the x coordinates for a second. This number here, r cosine A, represents how far the red point is horizontally from the origin. This down here, our blue point relative to the red point, represents how far, the x-coordinate represents how far horizontally the blue point is from the red point. If I add those two things together, I get the distance horizontally that the blue point is relative to the origin. So what we'll end up with is, so let's just write it down here, the blue point relative to the origin, we're going to have r cosine A plus r pi minus A cosine of A plus pi over 2. And the y coordinate is r sine A plus r pi minus A times, sorry about this, sine of A plus pi over 2. Okay, and that is our parameterization of the location of the blue point. All right, so let me quickly, let's just look at, that's exactly this parameterization. If you look over on the left-hand side of the screen now, here, I'll highlight it. We can see the x coordinate here is, so I've used a radius of 1, so r has been replaced by 1, but it's r cosine A plus pi minus A cosine of A plus pi over 2, exactly what we wrote over there. and then the sign is the same. I have to scroll through to see it. Sine A plus pi minus plus quantity pi minus A times sine of A plus pi over 2. Okay, and that exactly describes the path of the circle of the blue point on this left side of the circle. Okay, so there are other ways to come at that parameterization. I've done it in the past actually, and I had a different solution I was going to show, and I realized it was a little more complicated than it needs to be. I think this is maybe the most straightforward one I've come up with. However, we are not done. So let's do one more thing. Let's just go to some white space. So let me copy what we need. So the parameterization, all right. The parameterization is r cosine of A plus, where did it go? Erase this, plus r times pi minus A cosine of A plus pi over 2. That's the x coordinate. The y coordinate is r sine A plus r pi minus A cosine of A plus pi over 2. Okay, so I'm going to erase everything else. There was a way to make this eraser bigger. Let's just erase this so we have some space. Okay, so there's our parameterization. Okay, so we still need to compute the area. I'm not going to totally do this, but let's get it set up. The idea, we can think of this as our function for x. We can think of all this as our function for y, where A is the parameter. Right? Well, in terms of, oh, let me put in one more thing here. This is describing the path as theta goes from 0, sorry, A goes from 0 to pi. Right, as that, remember theta A was the angle between, so here's our pool. It was the last point of contact for the leash. So as the dog goes all the way around, that is an angle of pi. So A goes between 0 and pi. Well, when we're integrating over parametric equations, what we've decided or discovered the area was in previous videos, you take, you integrate over the beginning and end of your interval, and you have your y function times the derivative of your x function relative to the parameter. So in this case, it's going to be 0 to pi y of A times x prime of A dA. Now, it's going to be a little bit ugly, but it's not that bad. There's a bunch of constants floating around. We're taking derivatives with respect to A. What you're going to end up with are terms like this. Some kind of constant times sine of A cosine of A, right? I'm just going to write K1 for some constant. And you're going to have terms that look like some other constant times sine squared of, oh wait, sorry, I realized I'm mixing this up because of that cosine. So when we multiply, let's do a little bit of it. Sorry, I realized I was oversimplifying this. I'm still not going to finish all of it, but we can do a little bit of it. So if I take the derivative of x with respect to A, what do I get? I get negative r sine of A, and I get, oh, I'll have a product rule here, and let's see, so we'll have a constant, and the derivative of this first term is negative, so we're going to get negative, sorry, I'm trying to think of the easiest way to do this. I realized when I did this. Let's hold off on this for a second. I want to write it out simply instead of, I want to decide what the easiest way to do this is. But I actually think most of it's pretty straightforward. So we take our derivatives, we get a constant, we'll get an ugly-ish string of trig, and sometimes trig times the variable a. And I think we'll be using things like, there'll be substitution, parts will work on some of them. You'll probably need to use for some of them this identity and this identity to take those integrals, okay? I'm going to suggest on this is what I'm going to say. I'm not going to slog through all of that. This video is already long enough. Maybe I'll do a little write-up on it if I find the time. But all of them are doable. I'm kind of looking in my head at what's going to show up. They're all doable. They're going to take some careful consideration to get the derivatives down. But you can remember you've got a textbook for reference. These are probably old integrals that you haven't looked at in quite a while. I think you might end up with some things that end up with, you might need some trig identities to take care of this a plus pi over 2. There's some nice identities that will turn, oh yeah, that's what I would suggest. There are some identities that can turn cosines of a plus pi over 2 into, oh, I just realized I copied this one wrong. This is sine of pi over 2, a plus pi over 2. And the same thing for sine of a plus pi over 2 are your sum and difference formulas that will make these cross terms kind of connect in easier ways. So you'll get terms that will have, this is what I was trying to see before and I forgot about that part. You'll end up with things that look like this that you have to integrate, right? Some kind of constant. And you'll need to use a u sub, either sine of a or cosine of a will work out. And I think it's pretty doable. So try to get it there and then see what happens and we'll move forward from that. Okay, I'm going to stop this here. That's it for now. I'll talk to you guys next time.